So we kind of did, in the last lecture, a sort of change of course. You might have noticed the class up to then was all about the layer model, which makes perfectly good sense for global warming. And then greenhouse gases, it's obvious why we're doing that. And then all of a sudden we started talking about atmospheric pressure. Why do we care about atmospheric pressure, you may be asking yourself. The reason is when we draw this layer model, so we've done this a million times, so we'll do it with real gases in it, CO2, etc., so water vapor, freons, all those other greenhouse gases. Some of the light gets absorbed and re-emitted by the gases, others in the atmospheric window, if it's not a cloudy day, go all the way from the ground out to space. And then we sort of said, oh yeah, it's colder up here than it is down there. Now the real layer model, we could actually, it came up with colder aloft all by itself. Right, so there's the real layer model, and you calculate a temperature of the atmosphere and a temperature of the ground, which happens to be the temperature of the atmosphere times some number, which is bigger than 1, so it's warmer at the ground. And so in this layer model, it ended up, this was colder because of the radiation, the way the light carries energy around vertically in the atmosphere. So it kind of came out that this was cold and this was warm because of that. But this is a case of getting the right answer actually for the wrong reason. So the real atmosphere, it does get colder when you climb up in the atmosphere. And the reason why has to do, it sort of starts out with this business of atmospheric pressure. So we're going to start from there. And where we're going to go today is to learn why it gets colder as you climb a mountain in the atmosphere. And it turns out that that's really important to the global warming forecast. Because if we said that it wasn't that way, say if we said it's warm everywhere, then if you have infrared light coming from up here where the gases are instead of from the ground, it doesn't matter because sigma t to the fourth of warm is the same, it doesn't matter if it's all the same temperature. So in the layer model, for example, you did a question of nuclear winter, which is where the atmosphere, the sunlight gets absorbed in the atmosphere there. And in that case, actually, what happened was it got cold everywhere, but it's the same temperature. The whole greenhouse effect kind of collapsed if you didn't have a difference between the temperature up above where it's cold and down here where it's warm. So these gases are emitting IR, and the intensity depends on temperature. And so this has to be colder than the temperature of the ground if you want the greenhouse effect to give you any to work. So the temperature gradient is kind of an essential part of the whole greenhouse effect. And we kind of got it, from this layer model for sort of the wrong reasons. So now we're going to go back and talk about what the real reasons are. And it has to do with how gases behave as you change the pressure. So gases are expandable and compressible. So if you change the pressure, they expand and contract. That much we've already talked about. But it turns out when gases expand, they cool. So let's say you had a piston and it had a bunch of gas molecules in it. And those molecules are there at some temperature, which means that they have some kinetic energy. They're flying around with some velocity, and they're bouncing off the walls. And the bouncing is off the wall is what creates the pressure. So you're holding this piston in here with your hand and holding it. You're pushing against the gas. What you're pushing against is the gas molecules bouncing off the walls of that piston. If we now let this thing expand, so there are fewer molecules per volume in that piston because it's a bigger volume, same number of molecules. It turns out that the molecules slow down. So the way they always explain this, I guess it makes sense. It's the best way I know how to explain it, is that when this piston expands, it's kind of doing work against the rest of the universe. So one way you can experience this is if you've got your bicycle tire again, you've got it pumped up, but say you want to let the air out because you want to change the tire or something. So you stick a fingernail or a thumbnail down into the little valve where the button is that lets the air come out, so the air is coming out and it's rushing past your fingernail or something. It'll feel cool. You'll actually feel cold coming out, even though the air inside there when it was pumped up was at the same temperature as outside. It's not like you're riding around with refrigerated air in your tires all the time. But when it expands, it saps it of the kinetic energy and makes it cool down. Another way that this impinges on daily life, perhaps, is if you have ever done scuba diving. So you take your tanks into the scuba shop, and you got to get them filled up with air. So they got a compressor there, and they can fill up the tanks with air. But when you compress the gas, it heats up. And so heating it up increases the pressure. So if it's a shoddy dive shop, if it's just a crummy place, they'll let your tanks heat up, and then when you get it out into the ocean where it's cooler, it'll cool down and you won't have as much air, it won't have as much pressure as you had when it was hot. So the good dive shop will have a big tub there of water, and they'll put the tanks in the water to cool it down as you fill it up because of this tendency for gases. When you compress them, they heat up. When you expand them, they cool down. So I don't know if I would have been able to predict this from first principles, so I don't know if you should be able to or not, but you can kind of rationalize it or just understand it, or now we're going to make use of it. Okay, so, and then of course the atmospheric pressure changes as a function of altitude in the atmosphere, because as you go up you have less air over your head, less air that you're feeling the weight of, and because the gas expands you have this pressure as a function of altitude that does this exponential function like we talked about last time. Okay, now what is it that determines the temperature structure of the atmosphere? It turns out that what determines that is the process of convection. Convection is one of those 3 or 4 different ways of carrying heat around that we talked about in the very first lecture. It is basically where you have heat that comes in from below. So you get this sort of hot air, or you can have convection in water, which sort of forms sort of a blob down at the bottom where the heat is coming in, and the hot air expands because it's warmer, and when you put more thermal energy into those molecules, they're flying around faster, so they're pushing out against the rest of the world more intensely, so they expand. So now this same blob takes up a bigger space, because it's expanded, and then so it's less dense and it rises, and then another blob will sort of come down. So a lava lamp works by convection. You have these two different unmixable fluids, one that's clear and the other one that's like fluorescent pink or some color like that. It's sort of a blobby, oily stuff. And in the light bulb is always at the bottom of a lava lamp. If it was at the top, it wouldn't work. It has to be at the bottom. The blobs sink down right next to the light bulb. They heat up, they expand and rise, and so they sort of just do this like cycling thing up and down. That's convection. So the simplest case to understand is convection in water. So let's imagine a pot of water on the stove, and there's some depth, some water depth in the pot, a saucepan, a couple inches of water depth is all we need. And we're going to start out with the water in the pan being well mixed. So we're going to stir it up first. We're not going to, stratify it. It's not going to be like a black and tan where you have two different kinds of beer, one that's warm and cold. We're going to have it all the same. So it's all going to be the same temperature. So the temperature in the pan of water is going to be all the same. Now we're going to, so that's sort of the first part, the first stage of this adventure. The second is we're going to put some heat in at the bottom. So that means the temperature down at the bottom is going to rise up a little bit. So the temperature profile is going to just scooch up just a tiny bit, and it's going to happen right at the bottom because that's where the heat energy is being put in. So now this little blob of warmer water at the bottom of the pan has expanded, and it's now less dense than the water above it, so it rises. So it could, in a lava lamp, because it can never mix, this would be a blob of the lava, and it would just rise all the way up to the top. And there it would sit and cool down until it got more dense than the rest of the stuff, and then it would sink again. What happens in the atmosphere and the ocean, actually, is better approximated by saying that it mixes. With the rest of the fluid. So we're not going to let the blob survive all the way to the top. Instead, it's going to rise up, but it's going to mix. And so we're going to get a new sort of average temperature of the whole pan of water. So that should be pretty clear. Water is the easy case to sort of start with and kind of define this whole thing. If it's not clear, we'll talk about it. But if it is clear, then we'll talk about gases, which do all of this trickery with expanding and cooling and all of that. So we're going to add, kind of another layer of complexity onto this now if we're ready to go there. Ready as ever. Okay. So we're going to do the exact same sort of parallel case, but now do it with gases. So part 2. So we're going to start out, and we want it to be well mixed. So what does that mean? Temperature as a function of altitude in this column of gas. And it's all going to be the same kind of gas. It's all going to have the same kind of energy in it. So we're going to, mix it all up. So there's no differences. This isn't this gas and that's that gas. It's all the same stuff. But the gas that is up high is going to be in an expanded state relative to the gas that's down by the ground, because the pressure is lower up high and gases expand under lower pressure. So this gas, which is going to be totally well mixed, is not going to have the same temperature. It's going to have different temperatures. It's going to go like that. So if we were to take a blob of this gas and with our mixer, a fan or whatever, however we're mixing this, and raise it up, it would cool down as it rises up because it's expanding. So it would just follow along this trajectory like that. Or if we were to take some gas up here and then force it to go down, we're not putting any heat into it or letting any leave, but we just are changing the pressure. So it's contracting, and when you compress it, it heats up, just like the gas in the scuba tanks. You compress it, it heats up, and your scuba tanks get too hot. And so it comes down and it follows that trajectory. So these two parcels of gas are essentially the same. You could switch them and there wouldn't be any difference. They are at different temperatures because up here it's expanded and down here it's compressed. Cool? Let me get away with that. Okay, so this is analogous to this first one where we just have the same temperature in the water. Water isn't doing this trick because it doesn't care about the pressure. It doesn't expand or compress. To a first approximation, it's incompressible. So you're at the bottom of a pan of water or the top. The pressure is lower at the top, but the water hasn't expanded, and so it hasn't cooled down. The gas is expandable. Okay, so that's our first stage. The second stage is to put in a little bit of heat at the bottom, as before. And so the temperature gets a little hotter. At the bottom. So the pan of water, the burner is at the bottom. The atmosphere, the heat source is the sunlight, which comes through the atmosphere and hits the ground. When you did the nuclear winter, the heat source was up high, and so that kind of screwed everything up. It wouldn't convect if you had nuclear winter, because then the heat source is at the top. It's like it would be like a lava lamp upside down. Wouldn't do its thing either, because it has to be heating coming in from the bottom or else cooling from the top. Something that makes it unstable, makes denser stuff on top of lighter stuff. That's what makes convection happen. So we make this parcel warmer than the rest of it, this air blob, and so it tends to rise up. And as it rises, it tends to follow a trajectory like that. It's parallel to this one, but it stays warmer than the ambient air all the way up. So if this was unmixable air, like in a lava lamp, you could make a blob that would go all the way to the top, like the blob of lava. But in the atmosphere and in the ocean, just like we did in the pan of water, mostly what happens is it mixes, it rises and mixes. So it tends to raise the temperature all the way throughout the whole column of the air. So step 1 is well mixed. Step 2, put some heat in at the bottom. Step 3, rises and mixes with the rest of the fluid. The processes are all exactly the same, but all we're doing is just tilting it over to the side. That's sort of the only thing that changes because of this trick of expanding and cooling that the gas does. It sort of puts a slant on the whole thing, but otherwise everything is exactly the same. So the layer model had the change in temperature with height was set by radiation. Only radiation, the light, the energy carried around by the light. So there are some stars that where the temperature inside the star is set only by radiation. So it is physically possible to do that. But in our atmosphere, the change in temperature with height would be about 16 degrees C per kilometer if the temperature was just controlled by the radiation, the way we did it in the layer model. The real world atmosphere, the temperature gradient with height, this temperature gradient with height, it has a name. So I'm just going to define it for you. It's kind of an ugly name that will, turn you off. But, just look at it without flinching, and the pain will subside, shortly. But this is what they all call it, and I think I succumbed to using it in the text, and so we're just going to use the name. The name is lapse rate. Lapse rate. It's ugly, I know. But anyway, in the real world, the lapse rate that is observed, the real world is only 6 degrees C per kilometer. So you climb up a mountain, if the temperature was only set by light, and if there was no convection, you'd expect to cool down by 16 degrees C every kilometer that you climbed up in the atmosphere. And that turns out to be not right. The real world is only 6 degrees per kilometer. And that is because That is because 16 degrees C per kilometer would be unstable. It would just naturally convect. So here's temperature, and here's height, and I'll draw 16 degrees C per kilometer. And then I will draw how much the gas cools down when it expands. So I'll draw what happens when you let this thing mix. And it turns out that it's only 6 degrees C per kilometer. So that means a little parcel of air here, if it rose up just a little tiny bit, would be warmer than the air around it. So it's going to keep rising. It's just going to keep rising. A lapse rate of this 16 degrees C, if we sort of translate out of this confusing world where the gases expand and cool down and everything back into the nice, safe pan of water, the straight line is kind of analogous to the 6 degrees C in the air. And then this one would be like warmer water underneath and colder water up above. So that would tend to naturally mix. That would be dense water up here that tends to fall like a rock, and then buoyant water down here that tends to rise up. So just like putting cold water on top of warm water in a pan on stove would be unstable, it would be heavy stuff on top of light stuff. This 16 degrees change in temperature from radiation would be unstable. It's heavy stuff on top of light stuff, and it's going to want to turn. It's going to want to fall down. It's going to want to mix. So what we're after is this 6 degrees C per kilometer, but the convection that we just talked about would lead to something like 10 degrees C per kilometer. So the convection by itself is not giving us the real temperature of the atmosphere as you go aloft. There's a missing ingredient, which I will fill in for you now, if we're, understand where we're going here. So that missing ingredient is water vapor. So just to sort of remind you, if you take liquid water and make vapor, or you go from vapor to make liquid, there's a substantial amount of heat involved in that. We can actually write something like a chemical reaction. Liquid plus heat goes to make vapor. So we talked about this before, that if you stick your hand into the steam coming out of a teapot that's boiling, you'll burn yourself because the vapor hits your skin and condenses and releases all of its heat. So it's this heat that's kind of carried by the vapor that gets dumped when it goes to the liquid state. So this effect is now going to impact what happens when you do convection in the atmosphere. So the first thing we need to know is that the amount of water vapor that you can have depends very strongly on the temperature. So the saturated pressure of vapor is going to be a strong function of the temperature. So saturated vapor pressure, you've heard of this as relative humidity. So 100% relative humidity, when it's kind of all muggy and gross, that is where there is as much vapor in the air as the air wants to hold. And you try to evaporate some more water into it, and you might be able to do it a little while, but the water is going to want to condense out because it doesn't want to be 120% relative humidity or 200% relative humidity or something like that. It tends to lose the vapor to the liquid state. You make little droplets and they fall down, and so it tends to go back to 100% relative humidity. Or if the air is less than 100% relative humidity and you put a saucer of water there, the water will tend to evaporate and try to make the air 100% relative humidity. So there's a certain amount of water vapor that the air kind of likes to hold at a given temperature. So another thing we learned last time is that if you know the pressure of a gas, that is directly determined by the number of molecules. So if you have twice as many molecules, that would be twice as much pressure from that gas. So we can call this the vapor pressure. So that would be in units of atmospheres or bars or something like that. Or we could call this the water mixing ratio, which would be like parts per million of water molecules or something like that. So these are sort of equivalent units, either the pressure or the mixing ratio, just like it was for CO2 and nitrogen and things like that we talked about last time. Okay, so the point here of making this plot is that the saturation amount of water vapor you can have depends very strongly on the temperature. It goes up like that. So in warm conditions, you can have a lot more water vapor than in cold conditions. It just doesn't. So you've got liquid water, which is kind of in this very embedded, very close environment of the liquid. If you put a lot of heat energy into that, the molecules bouncing around like crazy. They don't want to be in that confined liquid state. so much anymore. You put enough heat energy in there, and they just want to break free and go into the gas phase where they're sort of freer. So you can kind of understand why warming it up would tend to make it go into the gas phase instead of the liquid phase. And then the ice phase is even more ordered. So you make it colder and colder, and eventually it's, gets tired of all this, chaos, and it wants to just settle down into a crystal. It sort of makes sense how the progression of the phases change as a function of temperature. Now, one thing that's interesting here is that it doesn't matter about the other gases. So let's say you had a box of water and there was air in there, and it's at some temperature, and according to the temperature there's going to be 10 millibars of water vapor in the air. And now we're going to do the same experiment. We're going to have water in there, but it's going to be a vacuum, like in outer space. It turns out that the water is going to evaporate and make the same 10 millibars of vapor in that vacuum as it did here. So when talking about this solubility changing as a function of temperature, it's real tempting to say that warm air can hold more water vapor than cold air can, because that's kind of how it looks to us, because there's always air around, and we just don't think about what it would be like if we were sitting here in a vacuum, because it would be kind of disruptive. But it's not actually the air. It's it's the water. It's a property of the water. How much of the water molecules want to be, flying around, and how much want to be in the liquid state. It's a function of the temperature, and whether there's air or not doesn't really make any difference. Okay, so let's say that we start out with 80% relative humidity. At the ground, at some temperature. So there's the ground temperature, and this would be 100%. And we're not there, we're just at 80%, so it's 8/10 of the way up. So there's 80% relative humidity. And now we're going to let the sun shine on the ground, and it's going to make the air right next to the ground expand and want to rise up. So it does that, and when it expands, when it rises up, it expands, and so its temperature drops, because that's what gases do. When they expand, the temperature drops, like coming out of your bicycle tire. And it's going to follow this 10 degrees C per kilometer as it starts to do that. But when the temperature drops, that means it's sort of moving in this direction. And so the same amount of water vapor that was only 80% relative humidity at that warm temperature, when the air gets colder, the same amount of water vapor pressure suddenly reaches 100% relative humidity at a colder temperature. So at this nice warm temperature at the ground, you could put more water vapor there before you'd get any condensation. It wasn't completely filled up. But how much it wants to be there goes down as you change the temperature. So at some height, so we'll say 80% relative humidity will be right there, and then 100% relative humidity is sort of right there. Now, if you raise up any further, you'd start to get to where there's too much water vapor. 110, 120, 130% relative humidity, something like that. It's more than wants to be there. And so these water molecules in the vapor phase are going to go, whoa, it's cold. I'm going to condense. And they're going to form droplets. So they're not going to go, they may go a little into this field, but not forever, not very far. So they sort of tend to follow this thing on down. And so as it cools down, you got to condense water vapor. And as you condense water vapor, you're going from vapor goes to liquid plus heat. It's giving off heat to the air. So the next stage, it sort of tries to cool down more because it's expanding, but condensation kind of adds some extra heat to that air. And so it's expanding, it's cooling down, but it doesn't cool down as much as if the air was dry. As a result, once you reach the point where the water vapor starts condensing, when you go up further, the change in temperature with altitude is sort of not as intense. So it turns out that with what they call moist convection, where as it's rising up, it's making cloud droplets, and the water vapor is dumping its heat into the gas, you get this change that is pretty close to what the real atmosphere looks like of 6 degrees C for every kilometer that you go up. So there's the answer. I mean, there's a lot of complicated stuff goes on in the atmospheric circulation, but to a first approximation, the temperature with height, which determines the strength of the greenhouse effect, because if there was no temperature difference with height, then it wouldn't matter where you put a pane of glass or CO2 molecules or what. It's all the same temperature. It doesn't matter. The temperature with height is determined by moist convection in the atmosphere. So if you just sit tight for another couple seconds, we can do some iClicker madness. Yay! OK. So you're flying in an unheated, unpressurized airplane. So as you go up higher in the sky, the air inside, which is the same as the air outside because it's unheated and unpressurized, gets what? It gets warmer, it gets colder. It gets colder, yes. It gets colder as you get higher up in the atmosphere. OK, so that was easy. Now, you're a fish, and you live in a well-mixed ocean. So the water is all well mixed. It's all the same stuff. And you're traveling in a submarine, which is unheated and unpressurized. And as you go up higher in the water column in the water gets what? Does it warmer or colder or no change? Now remember, this is a well-mixed ocean. So somebody just went in with a huge egg beater and mixed the whole thing up. So the real ocean, in fact, is warmer on the surface than it is at depth. But this is a well-mixed ocean we're talking about. So maybe a swimming pool or something like that. OK, I gave that one away. No change. You're right. All right. So you're the same fish, but now the submarine is pressurized. So you're some sort of deep sea fish, and you would explode if you got to too low pressure. So you build a submarine that holds the pressure in, and you go up to the top of the water, and you haven't warmed up or cooled down the water by heating or cooling, but you pump water into the submarine to keep the pressure right, and as you ascend, the water inside oh, what are you doing? No! Yes, there you go. The water inside doesn't change because it doesn't really matter what pressure you put on the water. It doesn't expand or compress. It doesn't, it doesn't feel the pressure. So you can't really change the pressure, the temperature of the water very much by squeezing it. A little bit, but not very much. So that's good. Next. You live on a planet with a dry atmosphere, like Mars. And the lapse rate, the change in temperature with altitude, is determined entirely by convection, the way we've been talking about. And you're flying in an airplane that is pressurized. So you go up high, and the pressure outside is lower. And the temperature outside is lower, right, because the air has expanded. But you pump the air into the airplane until it's at the same pressure as it was down at the ground. So temperature with height, temperature outside goes down as you go up because the gas expands and cools. But you take some gas from out here, which is very cold, and you pump it up to the pressure down here. What happens to the temperature is oh, you guys are good. You're way ahead of me. You should just yawn at me or something if I'm boring you, if you're way ahead of me like that. Yeah, so you pump this air up to the same pressure as down here, and the temperature goes back up, so it's the same as at the ground. OK, now here's the tricky one. Now we're adding water vapor to the atmosphere. You're not on Mars anymore. You're on Earth, and there's water vapor in the atmosphere. And the temperature as you go up in the atmosphere is determined by moist convection. So this process of the air expanding, the water condensing, dumping its heat, and then the water rains out, and then there's the air. So a pressurized airplane, the air inside is pulled in from the outside, but it's compressed until it's the same pressure as at the ground. So do you have to heat that air in that airplane, or do you have to air condition it? I'm going to let the turbulence in our concept here sort of die down for a moment, in hopes that you will realize that actually you have to air condition the air in the airplane. So let's say the temperature gradient with height is 6 degrees C per kilometer in moist convection. And so you're up here, and then you want to compress this air back to the pressure of the ground, but you're not evaporating water in it. The water has all rained out and gone away. So the air inside an airplane is always just incredibly dry. You ever notice that? You just get sort of desiccated. When you come back down, so this is 6 degrees C, and there's 10 degrees C. When you recompress the air down to the ground, it actually ends up being much warmer than the ground. So even though the air temperature outside an airplane is 50 below zero or something, when they compress it, they have to air condition it to keep you from cooking, because the water evaporated, dumped its heat, and the heat is still there. OK, great. See you on Wednesday.